This little county bridge that somebody's retrofitting, and this is the detail that comes across a fax machine, and somebody says, what do you think of that? Now, they're not going to put on a new deck. They know how to do the bottom flange, and somebody said, do you see any problem with this one? Yeah, I think you're starting to see the problem with that one, right? Let me tell you something about welders. First, welders don't think you're too smart because you're an engineer. That doesn't buy them any credit at all. One of the technicians at our company has a sign over his bench, and it says, you can lead an engineer to knowledge, but you can't make them think. In any event, the welder who looks at this says, what was that guy thinking? Because the welder has to get his head up here, he has to look up here, he has to bend the electrode and goober it in there. That's another technical term we use, goobering. That's what it's going to do. You know what the welder realizes? You know, if I can't see it and make it, the inspector can't see it either. You have no idea what you're going to get. Okay? Now, this may not be the prettiest thing, but it's another detail that's going to be a little easier for the welder to make. Number 9, you say, what happened to 4, 5, 6, 7, 8? Steve says I don't have time to do them, so I have to cut them out. Okay? On your critique sheets, say Steve should let me tell the whole story. Okay? On critique sheets, just say knock out the bolting portion and do welding all day. Okay? All right, good. Principle number 9, when possible, don't transfer major loads through the thickness of the steel. Steel is not fully isotropic. The property that really decreases the most in the through thickness dimension is the elongation or the ductility. This is a major stadium. This member here, the cantilevered member, is actually going to support seats. The designer is very concerned about lamellar tearing, and instead of having the loads transferred through the thickness of the material, they wound up transferring the vertical loads through the thickness of the material, primarily in compression, and then I had a continuous member that was subject to, it was bent to make this connection and minimizing some of the lamellar tearing tendencies. Principle number 10, provide a member when the forces change direction. This is pretty straightforward. You know from statics that if I had a member loaded up this way, that we don't have equilibrium, right? And I can go through the resolution of the forces. And the point is, to have equilibrium with these two forces, I need something in this direction. But too often we see engineers configure steel in a way that doesn't permit the application of the force that's required for equilibrium. And that would be something like this. Now, that's a structural knee in your building. And this detail that I'm showing here is exactly the same as what you had in that first figure where you can't resolve all those forces. Applying a member gives me a load path so I can resolve all those forces. You say, well, I know the web can do that. That's why the load gets concentrated in the web, and the flanges are not very effective when you don't have that diagonal member. So that's the principle there. We apply it to trusses, wide flange shapes going into a truss. Where's the vertical component of force go? Where does it go out here? Nowhere. And that's where adding in a stiffener to resist that load is helpful. All right, we're at a transition again. Any questions on what I covered there? All right, I have 16 minutes. We're going to get through distortion. And I previewed and promised you we might not get through cost reduction, or cost savings ideas, and we're not going to get through that today. Let's talk about distortion. You all know what distortion is. You started out with members located perpendicular one to the other, or welds placed, and it distorts. Distortion is the result of non-uniform heating and expansion, constraint, and subsequent cooling. To illustrate this, assume I have a block of steel and I put it in a vise. As I heat that block of steel, it has to volumetrically expand, but if the vise is rigid enough, it's precluded from expansion in that horizontal direction. When the steel gets ready to cool, it's free to shrink in that horizontal direction, and it will. So the block of steel that couldn't expand in the horizontal direction is free to expand in the contract in the transverse direction, and then I distort it or change the shape. Distortion has nothing to do with solidifying liquid material. Oh, there's a little bit of volumetric change, but at that strength, that temperature range, the steel has no strength. So that strain doesn't equate to any stress. It's only after the steel gets much cooler than that there's ample strength for those strains to cause movement in the part. So we have various forms: angular distortion, T-welds in a fillet joint. We could have double-sided fillet welds. That's the kind of angular distortion you would get. Angular distortion of a groove weld in a butt joint. We also have transverse shrinkage due to those butt joints. Not much, but a little bit. Contractors know beam to column connections typically shrink about 1/16 of an inch. They know that. They have to accommodate that in their buildings. So that's transverse shrinkage. There's also a longitudinal shrinkage. Everybody who makes plate girders knows that. If you make it 150 feet long, it's going to be a little shorter after you're making all those longitudinal welds. This is important. If the weld is below the neutral axis of the section, as that weld shrinks longitudinally, we're going to get a positive camber. Sometimes just knowing which way it's going to go is all you need to know. Conversely, if I weld below the neutral axis, if I weld above the neutral axis, I'm going to get a negative camber. So the orientation of the weld with respect to the neutral axis tells us which way it's going to go. And I'm going to give you 10 or 12 distortion control principles. The first one is use the smallest weld size possible. Everybody loses when you put in welds larger than necessary. It costs more to make, you have more cracking tendencies, more residual stresses, more distortion. So we don't want to put in welds any larger than necessary. And you know that. You put in a small weld, you get a little distortion. You put in a bigger weld, you get more distortion. You say, yeah, but that's your artwork. Okay, so I'll make 3 samples and I'll show you what you already know. The more welding you do, the more distortion you get. Now this one is not so intuitive. For a given weld size, you make the weld in the fewest number of passes. Unfortunately, sometimes people blend principle 1 and principle 2. And they say, well, if I want to limit distortion, I ought to make a whole bunch of small passes. That's just backwards. We want to make the weld in the fewest number of passes. Now the reason is that if I put in, let's say, 3 beads, I have 3 heating and cooling cycles. If I put in 10 or 12 passes, I have 10 or 12 heating and cooling cycles. And every time I heat and cool the steel, I add to the distortion that I'm going to see. There's my artwork. There's the actual samples. The top one made in 39 passes, the bottom one made in 6 passes. And you can see the difference in angular distortion. Principle number 3, make the weld with the lowest level of heat input. Now, heat input is an estimate of the amount of energy that goes into making a weld. We assume that all the voltage, E, and all the current, I, associated with that arc goes into the plate. And we divide that by the travel speed, S, and we get an amount of energy per unit length that's gone into that weld. Now that assumption is not right, because we know, you know, that when you make an arc, some of that energy is converted into light. Some of that energy is converted into noise. Some of that energy is used to make smoke that evaporates from the area. So we know that some of that energy doesn't go into the plate, but this tool is used to estimate the amount of energy that goes into the plate. Now, from a distortion point of view, what we want to do is, for a given weld size, we want to use welding procedures and processes that minimize the amount of energy that goes in. And the reason is this. We have to melt the blue stuff, but the extra energy goes into heating that gray stuff, the heat-affected zone. And some processes will introduce a lot more heat and create a lot larger heat-affected zone. If you've ever done any gas welding, you know that that puts a lot more heat into the part to make the weld, and you get a lot of distortion, a lot of warpage. And so there are differences in processes that will minimize the amount of heat-affected zone and consequently the amount of distortion. because that whole area expands, not only the weld metal but also heat affected zone, and then the whole area shrinks. And so if I have a large heat affected zone, I get more distortion than if I have smaller sizes of heat affected zones. Principle number 4, place the weld on or near the neutral axis. This is where you designers can help us. Here's a T section that I need to make into an I section. If I take a T and add in a flat plate, I put in the weld. Notice that the weld is below the neutral axis. As that weld shrinks longitudinally, I'm going to get a positive camber. Maybe you want some camber. Maybe that's good. But if you don't want camber, that's not an ideal arrangement. On the other hand, if I take 2 T's and I can put a weld on the neutral axis, that weld shrinks longitudinally, but my section stays linear. This is a little sample that we made up. You can see the warpage that's taken place over here. What you don't see is on the other side, there's no warpage at all. The sample became a good illustration of the importance of welding on the neutral axis. 2 pieces of steel, same size, welded to a channel. You know that the channel is going to shift the neutral axis over away from the center of the geometry of the part. The weld is put in between these 2 plates but displaced from the neutral axis by a short distance. Because of that short displacement, there's a bending that takes place, putting the left side into compression. That's why the buckling takes place, and the right side is tight. Balance welds about the neutral axis. Fortunately, this is pretty easy. Our symmetrical parts routinely balance the welds about the neutral axis, so the shrinkage of one offsets the shrinkage of another. So we tack weld it or fixture it together, do all the welding, take it away, and the shrinkage stresses of them will balance each other out. So is it with double-sided welds. I put in a groove weld on one side, the plates tend to V up. I put in a groove weld from the other side, it tends to bring them back. I continue to balance the sequence of welding, and I can keep alignment of the parts. That's exactly what I do in column splices. If I have 2 welders, I might put one on either side of the column, and the shrinkage stress of the two welds counterbalances each other. If I only have one welding, I do a little welding on one area, go to the other side of the column, do a little bit of welding, and keep my plumbness by cascading the welds around. Principle number 6. Well, this is my favorite principle. You say, do you have a favorite welding distortion principle? That's weird. I'm strange. So don't think this is so weird. This is my favorite. Balance the welds about the neutral axis. And we don't use this in every day, but here's the center of gravity of those 4 welds, and here's the neutral axis of this cross-section. So now I'm going to do what I normally don't do. I'm going to put in welds that are larger than necessary, so that this area of welding times the distance to the neutral axis is equal to this lesser area of welding times this greater distance to the neutral axis. And when I balance that out, I can control the shrinkage stress. I had a member 238 feet long that was non-symmetrical in both shapes. We adjusted the 4 weld sizes, put it in, it came out straight. People were amazed. It was beautiful using this principle. That's why I like it. Number 7, sequence assembly to balance the welds. This is a very practical one I hope you can use. If you ever come to one of our seminars in Cleveland, and we do those twice a year, and they're 3.5 days, and you learn about them on our website, we'll pull out the steel. We'll show you all these examples. Top flange 1/2 by 1.5 inches, web 1 or 1/2 by 1, bottom flange 1 by 2. It's 3 foot long. The center of gravity of the 4 welds is right here. The neutral axis of the section's here. You can see how far they're displaced. The first one we make up, we tack weld all together, we weld it all together, and we get a negative camber, and it's a visible bow in 36 inches. Now what can we do to do a better job? Look at the top T all by itself. Does everyone see that the center of gravity of those welds and the neutral axis are concurrent? So if I go back a couple of principles, if I weld at the neutral axis, I should be able to weld this up distortion free, right? So I make one of those up, and indeed that comes out to be the case. Now this has done all the shrinkage it's going to do. I don't have to worry about that one anymore. Bring that T in to the bottom flange. There's the center of gravity of the shape. There's the neutral axis of, center of gravity of the welds. There's the neutral axis of the shape. I'm welding on the neutral axis again. Fit that up, and it comes out straight. You say, yeah, but you designed that to come out that way. You're right. You're right. But we didn't design this one to come out that way. Now, this is a spandrel beam out of a building that's going to go into Kansas City. Loaded out on these surfaces are some precast panels. The architect's biggest concern is when you walk along the sidewalk and you look up those panels, they all look straight. Okay, whether the building stands or not, it's not a concern. But they surely don't want those panels sliding. Ooh, this is videotaped. I shouldn't have said that. Okay. Well, in any event, there's the configuration of the members. This is about full scale on the screen. This is 72 inches deep. Okay. 10 welds on here. The center of gravity of the 10 welds is here. The neutral axis of the section is here, and they're displaced by 2.39 inches. Without thinking about this, 150 feet long, without thinking about this, the fabricator tacked everything together and put in the 10 welds and had a 150-foot long banana because it took a great swing to the right. And you can all see why that would happen, right? So now the answer is how to solve the problem. We know what's shifting the center of gravity of welds over to the right. We know that it's these 4 welds on those L-shaped brackets. Unfortunately, in the L-shaped brackets, the weld's not on the neutral axis. So these 150-foot long members were cut into 75-foot long members and welded. Now that actually reduced the tip deflection by a quarter, or reduced it by 75%, to a quarter what it started with. Those were butt spliced together. They were a little bit wavy, wasn't too bad. Then those were brought in, welded onto the rest of the assembly. The neutral axis and center of gravity were close enough. They welded them up and were within tolerance of what they needed to do going forward. Principle number 8 says mirror components that have similar geometries. What's that? Here's a non-symmetrical shape, but let's assume I have to make a bunch of them. If I put those back to back, I create symmetry. Now the shrinkage stress of these welds will offset the shrinkage stress of these welds. The shrinkage stress of these offsets those. Now I have to have good, strong clamps or tack welds. When I'm all done and I break the assembly apart, I will have an elastic component of distortion. It won't be plastic, but there will be a little spring back there. And if that's a problem, I can, oops, I don't have it, I can offset it or preset it a little bit in the opposite direction. Principle number 9 says increase the torsional resistance. You know that open shapes don't have good torsional resistance. If I have a turnbuckle in this little assembly and I start to torque that up, those rods may initially shorten in size, but it won't take too long before they spring out of plane. Let's take that analogy and go over here to a channel, and I'm going to put a weld along the length of the channel. Does everyone see that as that weld shrinks longitudinally, it's not going to take too long before the channel takes on a twist? All right. What if I'm making a plate girder, and I put a weld on the flange, and that weld shrinks along the flange? Would that flange take on a twist? Would this flange and this flange take on a twist? And when I put a web in between, could I end up with an assembly that looks like what's on the right? I see some of you can't believe that, and neither could these folks. But you can see that it doesn't look very good at all. Now, laying on the horses, this is flat. What you're looking at is all elastic. And so it's probably suitable for service, probably not going to be a problem, but this is happening because you have an open shape that doesn't have a lot of torsional resistance. If you had a box shape, this would never happen, and if you had a box shape that was twisted after welding, you'll never get it straightened out because torsional resistance is so great. Principle number 10, I added to low on the list because this should not be the first thing you gravitate to. Presetting the parts so that after distortion they'll be straight. It's a very simple idea. Here we have a butt joint. We're subject to angular distortion. You preset it, and after you weld it, it comes back straight. Lots of ways you can pre-stress the material. Clamping the components, just keep them from moving in the first place. Could be fixturing, could be strong backs that you weld into the system to keep it from moving. If it doesn't move and cause residual or cause distortion, you won't have that problem to contend with. Finally, backstepping. Backstepping works when you have what I call rotational distortion. Here's an example where a building, this was in St. Louis, several stories of steel had already been erected, and the engineer was concerned about the column to base plate connection and ordered some stiffeners be applied. The welder had two kinds of wires, one for flat position welding, one for vertical welding. The welder went through and made all the horizontal welds first. Then they started making these vertical welds. As they made the vertical welds, the horizontal welds cracked. It really is a distortion problem because as this weld shrinks, it's pulling up on that stiffener. So the solution was to use a backstepping technique, lock this in so it couldn't rotate, and then weld into that and weld up into that, and the cracking problem was eliminated. Well, folks, we're going to stop right now. What follows in this particular segment is a description of or some estimates of distortion and how you can predict distortion. And then we have a little bit on flame straightening. And then, as I previewed, we have cost savings ideas that are afterwards, follows that. Now, I hope some of you are disappointed that we're not getting through everything. But there really is a good solution. If you get the design guide, you'll get the words that accompany this, and you'll have the background information in that. Not to oversell the design guide, but I wanted to let you know, again, what became what I think is going to be one of the most valuable parts of that is when we got the inquiries from the Solutions Center, we got a lot of questions on things like how do you extend rebar, welding on historic steel, welding on nuts, welding on bolts, and all the various array of problems that have been encountered, and we tried to tackle those. And there's a section, I think it's section 12, called Special Applications, where we take those one at a time and give you a systematic way to work through that. Section 14 of the design guide is on economy of welding and describes all of this last lecture that we didn't get to today. I hope you had a good time. I hope you thought it was worthwhile because you're not going to get anything out of the afternoon session. That's not true. Geoff does a great job, and so this afternoon you'll enjoy that. For those of you who think I'm rude, I normally don't leave right away, but I have an O'Hare flight at 1:30. And as much as I enjoy you, I enjoy my family more, so I'm headed on home. So have a good afternoon. Thanks for your attention. Thank you very much. Thank you.